Very good. All right. Well, thanks everyone for being here. I am very pleased today to be able to welcome Professor Gabriele Farina from MIT. He is a leading expert in multi-agent learning dynamics. He worked on this during his PhD at CMU, where he solved an open problem that I had been thinking about for at least a decade, where he came up with a polynomial time algorithm to compute something called an extensive form correlated equilibrium. And for this, he won a Best Paper Award at NeurIPS, and he also won the SIG Ecom, the ACM SIG Ecom, that's a particular SIG of ACM, the Doctoral Dissertation Award. And he was nominated also, and I think received honorable mention for the whole ACM Dissertation Award, so not just our particular SIG. So he is incredibly accomplished, now professor at MIT, and talking to us about his recent work that will appear at STOCK.
Wow, thanks so much. I don't know what to say. It's great to be here. Hi, everyone. It's good to meet you. I'm Gabriele. So today I wanted to talk about some recent results that we have at STOCK this year. This is based on joint work with Yorgos Piliouras and Ashkan Suleimani at MIT. And the goal of the STOCK is just like try to somehow trace the history of a particular problem, which is the problem of figuring out what are optimal rates for learning multi-agent multi-agent systems, and then just like try to tell you a little bit about like somehow some of the work that we have at STOCK that tries to go in that direction and tries to improve the bounds of what is known, and somehow like trace also maybe what's to come next after this. We're not quite there to optimality yet, but I think we're getting closer. Okay, but before we do that, let me maybe tell you a little bit about the, like what multi-agent learning is, just in case you're not familiar with it. And I think one way to think about multi-agent learning is that, it's a constructive answer to this very natural question, I think, which is, like suppose that you have a multi-agent interaction where you have agents that repeatedly participate in this, like at every time, like they act in this multi-agent interaction, and, like they gain some reward for doing it. That depends on their utility in the interaction, and then like somehow the interaction repeats again, and the players play again, and then this goes on for a while. The question is, are there rules that these agents can follow that allow, that enable them to refine their strategy after every match, so to guarantee, somehow mastering the game in the long run? And now mastering is a little bit of an overloaded term. Like somehow, it really depends what we mean by, solving the game, or solving the interaction. But, examples of what mastering might mean include at least the following. So, say that we're playing, we're one agent playing against stochastic opponents, meaning like opponents that always do the same thing. Okay, like mastering the game in this case would be that over time we're converging to whatever is a best response to them, like whatever is like our strategy that maximizes our utility against them. Now, the problem is that when the opponents are not stochastic, everybody moves, everybody's trying to learn. It's not really obvious what a best response by itself means, right? Because everybody keeps doing different things. But for example, like a goal in that case, say that you have a zero-sum interaction, so you have only two agents, and when one wins, the other one loses. One, like notion of mastering the game could be to recover, for example, a maximum equilibrium, or what people often call like a Nash equilibrium in the case of two players zero-sum. Yeah, and generally speaking, if you have like really many agents, somehow what we mean by mastering the game is recovering equilibrium. And I'll talk about what equilibrium means. It's a pretty, like intuitive concept, but somehow like keep in mind, like all of these three notions fall under this idea of mastering, and multi-agent learning talks about all three of these goals, for example. Okay, and why do we care about multi-agent learning as a way of solving multi-agent interactions? Like in particular, why learning and not, for example, casting the problem as like a big optimization problem and, just like try to solve it like monolithically as an optimization problem? Well, it turns out that this idea of learning, which means every player just like refining their strategy gradually, is currently the most scalable way that we know to solve large interactions. This has, like learning has been a key component in, like many recent breakthroughs. I have like here, for example, poker, where, for example, like people were able to build AI bots that bluff at poker better than humans. And the way they did it was like through kind of like learning. Basically, they set up, like poker agents that just like played against each other and refined their strategy until they converge to whatever is optimal bluffing, for example, in poker. Or, like here I have some work that OpenAI did on StarCraft. There's diplomacy. There's like some of the work that I did together with a lot of other people when it was a meta, where basically, we had in this case 7 players, and there's a language involved, and people communicate to each other, and somehow it's like a kind of like a war game where you have to make deals with people, and then support troops to just conquer part of the land. Also there, despite the language, despite the fact that we're playing with humans, using learning was what achieved us to achieve human level. And finally, these are recreational games, but there's entire teams in these tech companies that think about multi-agent learning in the context, for example, of auctions and markets, right? Where somehow, for example, Google, what they do is that when they have to bid in for advertisement slots, they treat this as I have like a bidder that's an agent that's participating with all the other bidders that represent all the other advertisers that are interested in showing ads in that slot, and they have these kind of like multi-agent dynamics that somehow decide how to bid optimally until somehow whoever bids the most, for example, gets the slot and so on, right? And you could imagine that that's another example of a repeated interaction where you want to learn how you should bid for ads, for example. Right? This is just to make the point that somehow, the first 3 were like recreational, but there's applications in economics that are not recreational. Okay, and why is multi-agent interesting? Well, I think, before we jump into the math and everything, but the very fact that we can do multi-agent learning, I think is very, deep in a sense, because it's really showing that there exists a deep connection between 2 things. One thing is, some local notion of every player just look at their own and just improves their strategy gradually, and something global, which is equilibrium, which just says that somehow over time the interaction of these players converges to an equilibrium point of this interaction, right? Somehow the fact that we can do learning means that something local is connected to something global. Okay, and usually these connections are not trivial, and it's not obvious at all that you would be able to just look at every player and gradually refine things until you reach some global equilibrium. Okay, and somehow this connection between local and global is very resilient, and it applies despite non-stationarity, despite chaos. Somehow, in this multi-agent learning problems, everybody's learning, everybody's updating their strategy. You end up with chaos, even in a formal sense. You can do chaos theory of these interactions, and despite all of this, you can still recover equilibrium. Okay, so for the purposes of this talk, the question that I want to focus on is, okay, we know that we can do learning, but how fast can we do learning? Okay, so in particular, what is the fastest speed that we can ensure this phenomenon of players doing learning eventually translating into extracting an equilibrium of the interaction can happen? At what speed can we extract equilibrium? Yeah, and just to set some notation, and what we mean by interactions for the purposes of this talk. It's enough to think of multi-agent interactions as the following model. Every agent has a set of available actions. Think about, for example, rock, paper, scissors. You would have rock, paper, or scissors, as an action to play. And then the way the interaction works is that when they play, the players just decide which action to pick from potentially a distribution over their available actions. So it doesn't have to be a deterministic choice. It can be just a randomized choice. And then they get a payoff that depends on the combination of actions selected by all players. Okay, so this model of interaction is what is called normal form games, if you're familiar. Now you might say, okay, these games really look like glorified multiplayer rock, paper, scissors, and just to some extent it's true, but you would be wrong to think that this is a very restrictive model. And in fact, even playing sequential games, for example, a game like poker, you can think of it that way. Somehow the leap that you have to, the mental leap that you have to make is just the fact that when you have a sequential game, what you call action really is just like a plan for the entire tree. So now your set of actions is an exponentially large set potentially, because if you have a tree, you can decide which edge to pick at every decision. Now you might end up with exponentially many plans. So in this case, for example, in this small game, there are 7, for the black player at the top can go left or right. If they go left, then, depending on what the white player does, they have to pick left or right here and left or right here. And they have to pick a choice for both cases because they don't control where they will end up at. So if a strategy for black needs to tell what they're going to do here and what they're going to do here. And, if the black player goes right, they can pick what to do at D. So you end up with 7 actions in this case. In general, it's an exponential number. Okay, but once you do this transformation, which makes, which kind of blows up the representation of the game from a tree to an exponential number of plans for the tree, then you still have an interaction of this form. Okay, and now you might be worried, okay, like, but this is an exponential blow up. I'm gonna have an answer for that. But like, long story short, the results that I will present depend only logarithmically on the number of actions. So it's fine to pay an exponential blow up at the beginning. You don't actually pay in the end like an exponential, dependence on the representation of the game tree. Okay, so with, I guess, the game model under control now, what is equilibrium? And equilibrium is exactly what you would expect. A situation of equilibrium is a situation where no player wants to deviate from this equilibrium. It's like we've reached a point in this interaction where nobody has any incentives to change what they're doing. Okay, now you can define different notions of equilibrium that depend on what the players observe, or like whether or not the strategies can be independent or can be correlated. There's like many notions of equilibrium. So if you've heard about correlated equilibrium and coarse correlated equilibrium and Nash equilibrium, these are just different, somehow specification of exactly what we mean by a situation in which no player has incentive to deviate. But by and large, the mental model you should have is just like we've reached a point where it's stable. Like nobody wants to change what they're doing. Okay, so Nash equilibrium is perhaps the most famous, most seminal notion of equilibrium. And in a Nash equilibrium, basically the players are just playing independently. So, you can think of, just like a situation of equilibrium as just like a profile or a tuple of independent strategies that the players can use, so that for every player, for every other strategy X prime that they could play, the utility for playing X prime is less than the utility for just like sticking to playing X. Okay. Now, Nash equilibria are complicated objects, but they become easy in two-player zero-sum games. And this is how, for example, heads-up no-limit Texas Hold'em was solved. They, just like try to compute a Nash equilibrium via learning. Okay, this heads-up basically means two-player, right? So in the, like the breakthrough in the casino where the bot was playing against the top poker pros, there was, like that bot was trained by doing learning on a two-player zero-sum game where computing Nash is easy. Computing Nash.
I have a question. What characteristics make it the case that the set of Nash equilibria is convex?
Okay, yeah, so that's a good question. There's a few ways of seeing it. You can either see it through the minimax theorem, that's usually like one way, but I feel like really what happens in two-player zero-sum games, like at a deeper level, is that there exists a collapse between different notions of equilibria, and in particular, coarse-correlated equilibria, which are, like always convex, and that's very easy to see, kind of like collapse to Nash.
What is it called, coarse?
Coarse-correlated equilibria. It's just like a different notion. That's like, because that one is constructed to be convex. That's one way to see it. But another way to see it is just through the minimax theorem, and that's because in two-player zero-sum games, computation of Nash equilibrium is the same as solving a max-min problem.
Zero-sum, I know.
Right.
It's just,
okay. Yeah, so what I was saying here is only for zero-sum.
Yeah, okay.
Okay, like beyond zero-sum, things are very complicated, and in fact, even topologically complicated, right? So this is like the set of Nash equilibria of a game that is two-player but not zero-sum. So even already for two players, you get not only non-convexity, but even somehow like topologically you start having holes in your set. Okay, which is even worse than having like a set that is non-convex but maybe like completely somehow like doesn't have holes. This one you can even have holes, and this is like a really nice example due to Kohlberg and Mertens. Right, so that's one of the issues. Like you start losing convexity as you move from two-player zero-sum to beyond two-player zero-sum, which means either two-player general sum or three players or more. Another bad thing that happens for us, at least as computer scientists, is the fact that you start losing the ability of representing your equilibrium using rational coordinates, right? So now also you're finally in the game of how do I even represent this thing? I suppose that I can compute it, but how do I even store it in a computer? And it's not obvious. And in fact, you can prove that for any kind of like irrational number, basically you can support it as like a Nash equilibrium of some game, right? So it's like this kind of like complicated results. This is only true for three or more players. The irrationality for two-player general sum is like this sweet spot where you lose the convexity, but you don't lose the rationality. And indeed, like two-player general sum games, are still hard, but somehow like they don't have both of these pathologies. So what makes Nash equilibria hard? I guess at this point we know that Nash equilibria are somehow intimately related to other important problems in computer science. So for example, Nash equilibria are Brouwer fixed points and vice versa. We think that computing Brouwer fixed point is complicated, which means that computing Nash in general, we believe is complicated. There's a really beautiful proof by Nash about why Nash equilibria are Brouwer fixed point that also proves the existence of Nash equilibria, because if you have a continuous function from a set to itself, then it must have a fixed point. That's how you prove that Nash equilibria exists. And Nash got the Nobel Prize for his work on equilibria. And it's a really beautiful, like if you've never really read Nash's, he has two papers. In one, the proof is pretty complicated of the existence, but in another one, like in a follow-up, he really cleans it up, and I think it's very pretty. So, if you are in the mood for like reading old papers from the 50s, I feel like Nash's paper might be like a great candidate for your list. Right. So okay. So what we said is, in two players, there are some games, probably Nash equilibria are what we want. Beyond, we have all these issues, the topology issue, the rationality issue. So long story short, we don't really care about Nash equilibria beyond, or like maybe that's not what our focus should be. Beyond two players, there are some games, and instead there we look for cores, correlated equilibria. The definition of course correlated equilibrium is exactly the definition of Nash equilibria, except that instead of saying that the strategies are independent, we allow correlation between the strategies. So it's like exactly the same formula. The only thing that has changed is that the xi's do not need to be independent between the players. The players can play in a correlated way. And you can think of course correlated equilibria exactly as the convexification of the notion of Nash equilibrium. It doesn't mean that the set of course correlated equilibria is the convex whole of the set of Nash equilibria, but somehow as a formulation of the problem, you can think of it as the convexification of the problem. Okay, and now that we know both the model and the notion of equilibrium, let's just maybe try to think about what is known about learning. Okay, and in particular, like we said, learning means that the players have a way to gradually update their strategies until equilibrium emerges. And one thing that's very important is, somehow to mention when we talk about this process is that we're interested in uncoupled learning dynamics, which means that somehow this this extraction of equilibria from a local process, basically like this extraction of a global concept from a local process, happens even if the local learners, like the individual players, only know about their own utilities, but not about anybody else's. Okay, so like it's important to know that somehow when we're saying that the agents learn, it's not like the agents are simulating what other agents are doing, or it's very different from doing monolithic kind of like offline optimization. Here, every learner is doing on their own. They have their own utility. They don't know the utilities of everybody else. They're just trying to update their strategy gradually based on what everybody else is doing. As you can imagine, this is very chaotic because now I update my strategy because of my utility, and somebody else has updated their strategy because of their utility. And now, maybe updated the strategy in one direction, but now the other players have changed, and so now I have to undo my step in the next iteration, and so on. So it's really not obvious that you can extract equilibrium. There is a popular formalization of actually what is even the goal of learning, right? Like in this kind of like chaotic landscape, it's not even obvious then what does it mean to have succeeded in learning. And the standard answer that we have today, which is, I think, a very versatile, kind of like really nice, crisp mathematical formalization, is the notion of regret minimization. And the idea of regret minimization is just to say that, okay, what it means to learn for every player is just that every player wants to minimize the maximum regret that they accumulate on each of the actions, where regret is a measure of how much they, in hindsight, hoped that they had played that action over and over, like for the entire past, instead of doing what they actually did. Okay, so mathematically, the regret of an action A is that quantity that you have on the right. It's like the sum over time of the utility of A minus the expected utility that the player got. Okay, now if you have high regret, it means that you want to play more that action. Somehow like regret can go both ways and people sometimes get confused. But regret in this case means if we have high regret, we want to play more. It's not that we regret playing it, it's that we regret not playing it. Okay? So exactly, so high regret, I wish I'd played that action all the time in hindsight. And now, what we care about is, somehow we look at all of our actions, we look at the regret that we've accumulated in all the actions. We want to keep as low as possible the maximum of these regrets. Okay. Now, one thing that's very important to know, and it will be important for later, is that a very good learner can have negative regret, And that's because regret is a measure of how much I wish in hindsight I could play action A all the time. And it's possible that because you were learning so well, actually there's no action that you want to play fixed all the time in hindsight, right? You might actually be, maybe you were lucky and every time you just like kept picking whatever was best for that round, okay? And so it's somehow like you gained from the fact that you could every time switch your action, whereas regret is only going back in time and just like saying, with the benefit of hindsight, if I fixed to one action all the time, how much I would have gotten. Okay, so regret can be negative, and that's usually like a paper cut that people that do not do regret minimization often run into. So, and this will be important in a second. Okay, now it turns out that we have many algorithms that can achieve low regret. Where low regret really that somehow what is the lowest regret that you can achieve? That's part of the like the motivation for the talk. But like at a minimum, what you would want for a good learner is for the quantity of regret to scale less than linearly with time. Like if you just do bad decision all the time, your regret is going to scale linearly. Okay, like if you want to be better than like being bad all the time, then you want the regret to scale sub-linearly. And it turns out that we have plenty of algorithms that guarantee a regret that no matter what happens in the game, no matter the number of players, no matter what the players are doing, always guarantees regret that is of the order of square root of t instead of t, right? So it's just like t to the 1/2 instead of t, okay? And these algorithms, I think, are pretty natural in the way they work. There's two categories, I would say. One is the regret tracking style of algorithms, which basically what they do is that they keep track of the regret that they have against all the actions, and then they prioritize based on whatever action has the highest regret. And then there's the descent style type of algorithms, which what they do is that they keep track of the strategy, and then at every time they observe what everybody else has done. They take the gradient of their own utility and they move their strategy a little bit in the direction of their gradient. Okay, so this is more like gradient descent. This is a little bit different. This is more like if I have high regret in action, it means I wish I could play it more in the past. Then I'm going to play more in the future. Okay. So just to give you like a few names and like just like a brief introduction for regret tracking algorithms. There are many variations. Now, the most standard, the first thought that you might have about how do I prioritize actions based on the regret is that you can just say, okay, at every time I'm just going to play whatever action has the highest regret. Okay, this exists. This is called follow the leader. Leader is just a term to say the action with the highest regret. Follow the leader is actually not a no regret algorithm, and the problem is that it can jump around too much. Like maybe you play one action, then you realize it's bad, now you want to play another action, then you keep jumping between actions. So it jumps around too much. It doesn't actually have a no regret guarantee, which means that it's not able to guarantee that in the worst case, the regret will be sublinear. Okay? But then, like the next following idea, other than just play whatever has the highest regret, might be play proportional to the regret. This sort of works. You just need to be careful that regret against some actions might be negative. Okay, so in fact, if you want to fix this idea, you just should just randomize according to the max between 0 and the regret. So you just like threshold the regrets, actions with negative regrets. You don't play actions with positive regrets. You just play proportional to how much positive regret you have over them. Okay, so this algorithm exists. It's called regret matching. This algorithm, or like a slight variation of this, is what was used, for example, to solve poker. Right? So internally, they used an algorithm that looked a lot like this. This algorithm has a very nice property, which is that it has no learning rates. Right? Like there's no parameters that you have to tune. You just play proportional to the regret, or I guess max between 0 and the regret. Okay, so it's a very popular algorithm in practice because it has no hyperparameter tuning that you have to do. It's not the only way that you can use to prioritize action based on regret. You could also, for example, do multiplicative weights, which what it does is that you now play proportional to the exponential of the regret multiplied by some learning rate. So unfortunately, multiplicative weights update has some learning rate. In practice, we know how to pick the learning rate in a way that theoretically guarantees sublinear regret. And in particular, for both of these algorithms, we have very concrete bounds on the regret that they achieve in the worst case. For regret matching, we have a regret that's bounded by square root of t, which is the number of rounds of learning, times the number of actions. Multiplicative weights has, in theory, a way better dependence on the number of actions, which is square root of t times log of the number of actions. And this will, if you remember the thing that I was saying about trees and an exponential number of actions for trees, you see now why that might not be a problem after all, right? There's like this log number of options.
I'm getting the opposite. When you talk about that example, I thought, okay, he's talking about computation.
Mhm.
You can avoid the runtime depending exponentially.
Mhm.
But here in regret, it still could be quite bad.
The computation.
I mean, it could end up being effectively growing with time, right? The regret could this.
Oh yeah. Regret grows with time. I mean, there's no way around it, though, right?
No, but I mean, if you grow super linearly in t, depending on the number of actions.
So are you saying like if the number of actions somehow depends on time?
Yeah, I mean, I guess if they're both functions of some n, then asymptotically, it can
I see.
end
Okay.
up being effectively super linear.
Right. Yeah. I don't think you should think of time, though, as part of the specification of the input. Right? Somehow time is something that we will pick later, and as we do more rounds of learning, we'll extract a better equilibrium. But somehow, like I feel like this t, like let's just maybe think of it as not part of the input, right? Like, and unfortunately, like there's no way that we can have in the worst case a dependence on t that is better than square root of t. It's actually known that there's a lower bound, but actually part of this, part of the result that I will talk about actually shows that in multi-agent learning you can get a log t dependence. So somehow like this worry is fixed for.
What is it? What if you did the worst thing at each moment? What would be the regret then?
If you as a learner always did the wrong thing, I mean it'd just be linear in time.
Yeah, so it'd be t.
It would be t. Yeah, it would be t.
But this bound could be worse than t if depending on the relationship between t and a.
Depending on the relationship between t and a, yes, I think so. But I feel like we shouldn't think of a and t as like related. Okay. Just like think of a game that's given. We have the number of actions, and then t will pick later depending on how good an equilibrium we want. Okay. Great. Okay. The descent style algorithms, similar to gradient descent, and in fact, online projected gradient descent is a descent style algorithm. And again, it has a very concrete regret bound that again scales linearly with the number of actions. Okay. Again, like these are regret tracking algorithms. These are descent style algorithms. The best algorithm that we know of is multiplicative weights update, which is a logarithmic dependence on the number of actions. Okay. Now it turns out that because of this square root of t dependence, you can just do the math, you can just invert the formula and figure out that, like the conclusion is if we want to, compute equilibrium, what we can do is that we can just, if we want epsilon approximate equilibrium, what we can do is that we can just let the learners play against each other for roughly 1 over epsilon squared. I'm hiding all the dependence on number of actions, so I'm just like only showing the dependence with epsilon, but roughly 1 over epsilon squared rounds of learning. So you want epsilon equilibrium, you do 1 over epsilon squared rounds, and like you can recover your equilibrium. Right? And here I have like 2 simulations of OGD, which is like online gradient descent, which is the descent style type of algorithm, and MW, which is multiplicative weights update, which was the regret tracking algorithm with like the log dependence on the number of actions. And they behave a little bit differently, but overall you can see that like in this game there's only one equilibrium, which is here. You can see somehow like it's like the fixed point of like this kind of like gradient field, and you can see that both algorithms circle around it, so that like the average strategy kind of like converges to the equilibrium.
Vector field is utility.
Yeah, like the vector field here is the same vector field of the Nash function, right? The one that was proving that fixed points of the vector field are Nash equilibrium. So, but you can think of it as basically, like the utility. All right, sounds great. One important thing is that usually what converges to equilibrium is the average strategy. Right? So the brown points are the actual strategies played by the agents. The gray dots are the averages, and the averages converge. And I'm going to talk a little bit about what happens if you actually want the day-to-day, brown points to converge, and some results are known. Great. Okay, but just to get back on our quest here, like the point of the talk is, can faster algorithms be designed? Right? Can you basically do better than 1 over epsilon squared? And long story short, the answer is yes, and you can do 1 over epsilon. Okay, and this is true no matter the number of players, no matter the number of actions. It's a very general result. Okay, but it's very important to know that like this yes has some caveats. The first thing is that you cannot hope to do better than 1 over epsilon squared in like under all circumstances. And in particular, the thing is that if all your opponents are playing completely at random, there's no way you're going to go faster. Like you can prove that there is like some lower bound. So somehow to get to this faster convergence, you have to have some form of collaborative kind of opponents, which doesn't mean that they're out there to help you, but at least it means that they're not out there doing whatever, like random at every time, right? There has to be some understanding that, for example, all of us are learning what is good for each of us individually, which might, like not be the same for everyone. But, somehow everybody's trying to learn this game instead of just like playing at random. Right? So there also has to be some agreement, if we want this to be possible, that the non-stationarity of the system is not completely unpredictable or adversarial. Okay? And somehow, basically, what we end up in is that, okay, like in general, for an adversarial setting, we cannot do better than 1 over epsilon squared. But for a non-adversarial setting that is nonetheless non-stationary because everybody's learning, we can do better. And the gap here is very subtle, and it has to do with the fact that even though like the environment is very non-stationary, when everybody's learning, the environment is not completely adversarial either. There's like this narrow gap that we want to exploit. Okay, and the reason why the environment is not adversarial is that somehow when everybody learns, the strategies move slowly, and so we have this kind of like smoothness going on in the system that we want to exploit as a form of predictability to produce better algorithms. That's kind of like the intuition. Okay, so we're kind of like in the business of exploiting somehow the fact that everybody's learning, which makes the multi-agent interaction smoother than what it could be in the worst case if everybody was acting adversarially or randomly.
Are you allowing the opponents to actually do this monolithic computation?
No, everybody's just doing their own. And also we don't know, it could be any number of players, could be any number of actions. Right? So we want to do it in generality. Yeah, like I said, like this key idea is to exploit some form of smoothness, which is by itself a form of predictability. Yeah, and there's this idea that goes back to the 2012, 2013, which is the idea of optimism, which is the fact that when like everybody's learning, somehow it's easy to anticipate the next gradient of your own utility, because if you're being optimistic, you just think that everything is going to move slowly, or maybe that you're close to equilibrium, and somehow you think that your next gradient, like the next gradient of your own utility that you will see, will be very close to the current gradient of your own utility, just because everybody's moving slowly. Okay? And you can design algorithms that are called optimistic regret minimizers. And usually, somehow exploiting this optimism is just a one-line change implementation. So, this is, for example, what optimistic multiplicative weights update, the update rule, looks like. If you remember, for the just like regular multiplicative weights update, you just don't have this additional term on the right. You just have eta times r. But now you add this kind of like differential term. That's a form of, if you want, people also like to call it negative momentum, that somehow helps to exploit the fact that you expect change to happen gradually. And, like I said, you can think of this as a form of negative momentum, and here it's like a simulation, and you can see that when you start going from non-optimistic to optimistic, the dynamics have like this kind of like almost like attraction towards the equilibrium. That is, again, like this form of like negative momentum going on. Okay, so yes, maybe like a good mental picture of what's going on. Now, at the analytic level, how do we analyze optimism? There has been like a lot of work. There was like a best paper award in 2015 by Serganis et al. That showed that one way of really crystallizing the analysis of optimistic learners is to use what is called an RVU bound. Just like putting it here just in case you're interested and you can go read about it. But fundamentally, what RVU bounds mean is that you can prove that the regret now, if you use optimism, scales with the square norm of the distance between consecutive utilities. Okay, so really, if the utilities change slowly, then that term will be very small. If you can bound it appropriately, you can even prove that this entire sum might be less than actually, depending on time. Yes.
The regret bounds harken back to the predecessor multiplicative weight algorithm, which is these pack and covering bounds. I don't know if you know about this, but then which do suffer from a 1 over epsilon squared lower bound, but then there's this Nesterov type technique in optimization which looks a lot like this.
Yeah.
This seems like it's linked to Nesterov.
That's a great question. Yes, indeed, I like to think of this as what happens in offline acceleration, right? So like Nesterov acceleration was like this big thing that also was mysterious for a while, and then people have a different way of thinking about it. But fundamentally, it is like this kind of like momentum term that helps, like go from, for example, for smooth optimization from 1/t to 1/t squared kind of dependence. Where it is a number of iterations of the method. Here is something similar. You go from 1/√t convergence to 1/t convergence into player zero-sum games. And I think the idea is also reminiscent of that, right? There is like this momentum kind of term going on. I would say that the difference maybe with Nesterov is that we want to do this for any number of players in a very decentralized way. And so you can think of this as maybe like an online version of that that's a little bit more complicated because you have a lot more non-stationarity going on. And it's not like you have one function, one gradient, and you're trying to get to the minimum. Here it's like a moving target, right? But nonetheless, I think it is reminiscent of that. Cool. So how is optimism useful? Well, the most important consequence of optimism is that you can prove that at all times, the sum of the regrets of all the agents, when everybody's being optimistic, is bounded by a constant. This is true for any number of players. And for two players, there are some games in particular. This means that if you now take two optimistic learners and put them together, Nash equilibrium can be extracted at an improved rate of 1/t instead of 1/√t. Right, so you only need, another way of saying it is that you only need 1/epsilon rounds of learning to get to epsilon equilibrium as opposed to 1/epsilon squared.
Yeah, I'm trying to interpret this as a theorem, and obviously there has to be some conditions, as you said, about the game itself. About the fact that all the players are learning or something. There's some condition to make this a theorem.
So you need that everybody is using optimistic dynamics. Optimistic, optimistic learning. You don't actually really need to know exactly what algorithm.
Is that it? I mean, you have any limit on how non-stationary the thing can be?
Yeah, you don't need it.
Kind of continuity or anything?
You don't need that. Yeah, I know it's pretty amazing. And here's actually the proof. I guess like a sketch of a proof. Yeah. But fundamentally, the RVU bounds just tell you that you remember, like you scale with the change in utility. There's also a term that I didn't say, which is also you have a negative term that depends on how much you're moving. And so now if you write these RVU bounds for both players and you like somehow have like bounded utilities in the game, then this sum will cancel with this sum and this sum will cancel with this sum. And so you just you get all these kind of like cancellations and you end up with sum of regrets is at most a constant. And this is kind of like the sketch of the proof. And really the heavy lifting is done by this RVU bounds. The problem is that knowing that the sum of regrets is bounded by a constant is very useful for Nash equilibria, but it's actually not really useful for more than two players zero sum. It's not very useful for coarse correlated equilibria. And the problem is that convergence to coarse correlated equilibria is not driven by the sum, unlike Nash equilibrium in two players zero sum games. It's driven by the maximum regret. And so even though you might have a sum that is constant, your worry is that you might have one term that's very positive and one term that's very negative. Okay, and so because you now scale only with the max, the term that's very positive is actually what drives your convergence, and so you don't have a good bound. Okay, so this is what happens, right? Exactly. Like the worry is that one player might be doing extremely well, which means very negative regret, like they don't regret anything, so very negative regret, while the other players are having a hard time keeping up, and because of that have a large positive regret. Okay. Nonetheless, there have been many breakthroughs here. Let me just mention a couple. This is the Surganis paper that I mentioned, which showed that for multiplayer, you can nonetheless get a dependence on time for the regret that grows as t to the 1/4 as opposed to square root of t. So that's already better by kind of like a square. In 2020, Chen and Peng improved this t to the 1/4 to t to the 1/6. But this only applies to two-player games, whereas this result was for any number of players. In 2021, Daskalakis et al. Had this breakthrough result that showed that actually for the first time, we can actually depend polylogarithmically in time. Okay, their analysis is based on multiplicative weights and it's very complicated. It has to do with higher order smoothness, they do Fourier transforms. I think it's not really obvious to me exactly what parts of it can be generalized easily or improved. Also, the constants are very big. But nonetheless, this was like, it's amazing that this is possible. It's like the first time that we actually didn't depend polynomially. And this somehow opened the door to trying to improve and understand how much more general this result is, and if we can even improve both the constants and the log, and make somehow like better algorithms out of this better understanding. And in 2022, we set out to understand exactly this. And one thing that we showed is that actually this fact that you can get logarithmic dependence on time is very general. Okay, and it applies to any convex set. And in particular, we showed in 2022 that in fact, for any convex set, you can do this kind of like general Nesterov acceleration, basically, and do, get like a logarithmic in time dependence in regret. Again, like this is like for any number of players. In fact, it's not even for action set. This is just like if your strategy set is just like whatever, some convex body in space, you can still do this. Yeah. Now, it turns out that unfortunately, the caveat with this result is that while it's very general, much simpler than this as a construction, it suffers a dependence on the dimension, which I guess in the case of multi-agent learning is the number of actions of each player, that is linear instead of logarithmic. Okay, so this is not very useful for, for example, for games played on trees, because there, this dependence, then the dimension is exponential in the size of the tree, as we said. Okay, so this is great for general sets, not great for action sets of games. And so this is what I want to talk about today. And like the math is a little bit complicated, but there is a way to fix the construction and still have logarithmic dependence on the number of actions. And the idea is that if you remember, the worry was that we were worried that one player might be doing extremely well and have large negative regret, while the other players are having a hard time keeping up and have large positive regret. And so the idea was, okay, what happens if we just try to prevent that by making sure that when players are doing too well, or like are starting to do too well, somehow they kind of like become less smart and start playing more and more uniform, for example, so that they kind of like incur more regret as they do that. Okay, so basically we want to dynamically pace down learners as they're doing too well. And we call this, instead of optimism, cautious optimism, because you just don't want to get too much ahead of yourself. Okay, and so basically this idea is not completely new in the sense of like the way it's done and the math, that's very new, but somehow like this idea of agents changing behavior depending on how they feel in the game has been historic, like since the beginning of the field of multi-agent learning. And somehow like this idea is reminiscent of maybe also like this other principle of win or learn fast by Bowling and Veloso, that if you see it's like from the 2000s. But it's like somehow like these ideas had never really been able to be exploited in math. Like these were just like ideas of how should good learners behave. And doing math on this was not easy. But the cool thing is that it is possible to just like give an analysis of this if you're being careful enough. And just like long story short, this is what we get now, and this is like the stock paper, right? So we get dependence on time, which is logarithmic. So we improve from log to the 40 to log t. Dependence on the number of actions, that is log squared. So we kind of like lose a little bit compared to this, and then depends on the number of players. But this construction applies to sequential games as well, for reasons that maybe I'll hint on briefly, and also is very general. Somehow, like the analysis compared to this, the analysis of this, I think, is like a lot more, like a lot easier. Yes, this is what we get. And let me just tell you a little bit of how this idea of pacing down learners works. So the idea is that on top of the learner, we just place this learning rate controller, which fundamentally solves this optimization problem, right? So lambda t is the learning rate of the player. And the learning rate is decided by taking the argmax of some constant that is roughly of order log squared d, and that's why we end up with log squared d in the bound, times log of lambda plus the log sum exp of the regret of the player against the actions. So you can think of this as basically like some form of like max regret. Like this term is very close to being like the maximum regret. And so basically the idea is that if if all the regrets are positive, the best thing you can do is just to maximize this. You'll have that this quantity is positive in lambda. So to maximize this, you'll just want to crank up lambda as much as you can, so get to some epsilon, because you want to maximize the first part. Okay? But if the maximum regret is negative, this quantity on the right scales negatively with lambda, right? So if you crank up lambda, in fact, what you end up with is that you actually are losing value. And so basically, you can prove that as the maximum regret goes more and more negative, the optimum of this will be lambda closer and closer to 0. Okay, where I guess, like there's also some hyperparameter eta that tells you what the maximum lambda should be. But basically what we're saying is that if for each player, the maximum regret across the actions is non-negative, then basically we just like learn at maximum speed that we can, so eta. But then as we're doing more like better and better, we start pacing ourselves down until we go to uniform strategies, playing it every round in the limit. And all of these processes completely uncoupled. Like we don't need to know the utilities of everybody else. What will turn out is that if everybody does this, somehow this kind of like trying to pace themselves, then equilibrium will be faster to reach for everybody involved. Okay, so this is what somehow like the solution to the learning rate control problem works for two actions. You can see like this is regret against the first action, this is regret against the second action. As the regrets start becoming smaller and smaller, the learning rate decreases and decreases. Now, doing the analysis of this is pretty complicated because these level sets are very non-convex. The problem at the top is also non-convex. I guess non-concave in general, and so it becomes concave if alpha is large enough. But a priori, that problem up there is like not like in the obvious class of problems that we know how to solve. Okay, but nonetheless, we will show that we can solve it. But the final algorithm is very simple after all. We just like for T rounds of learnings is like for every player, from the point of view of every player, we just keep track of the regret. If the maximum regret is high enough, we just decide that we're just gonna learn at full speed. Otherwise, we solve the learning rate control problem, and then we play strategy, which is what optimistic multiplicative weights would have played with the specific learning rate that comes from the learning rate control problem. It's very simple, just like one line change. Basically, the only thing that changes compared to multiplicative weights is that the learning rate changes, and it changes in a really non-monotonic way because, as you can imagine, during the game, our regret goes up and down. So it's not the standard, monotonic learning rate control that you would do, for example, for finding the Lipschitz constant in an optimization problem. It's not that kind of learning rate control. This is like a very different type of learning rate control that is non-monotonic. Now, the analysis fundamentally boils down to studying certain spectral properties of this learning rate control problem. A key technique that we use is self-concordance. So it turns out that the learning rate control problem is a self-concordant problem. And self-concordant functions have very strong spectral properties. So you can think of them as like some intrinsic second-order smoothness that really helps analysis. So if I were to kind of like pick one secret ingredient somehow that makes this entire 40-page proof go through, is I would say like somehow like this, knowing the self-concordance really helps. It's not the only thing. There's like a lot of like other important ideas, but somehow like for this paper at Stock, self-concordance was like a pretty important part of it, and very different from what people usually do in online learning. So let me just remind you of what self-concordance means, just in case some of you are not familiar. This is like an important class of functions that come up in linear optimization. They're related to barrier methods. But fundamentally, self-concordance is a property of functions that says that somehow like the function is almost quadratic around every point, roughly. I guess maybe that's one way to think about it. There's like a lot more, but somehow if you want one mental picture, maybe it's that. The difficulty is that like somehow the way we measure quadraticness, like there's like this notion of local norms. You have to be a little bit careful what you mean, but maybe that's one way. Like somehow like the Hessian variation is kind of like bounded. Like if y is close to x, then you see that the Hessian at y is bounded by multiples of the Hessian at x, right? It's roughly the mental picture. Now for 1D functions, it's known that self-concordance is basically equivalent to this condition. So like self-concordance is like, I think I would say one of the gems of nonlinear optimization, kind of like one of the masterpieces of Nesterov and Nemirovsky. Really cool theory. So forget about my talk, forget about like multi-agent learning, but if you're interested in nonlinear optimization, self-concordance, I think is a really beautiful kind of topic. It's kind of like cool, I think, that it also comes out naturally in multi-agent learning, which is instead what I'm interested in. Great. So, self-concordant functions have very strong properties. You can basically tell how close you are to the minimum. You can, somehow like doing Newton's method on self-concordant functions converges incredibly fast, like, log 1 over epsilon kind of speed. So, we use all of these properties in the proof. It's not obvious at all why the learning rate control problem would be self-concordant. In fact, it's not really obvious at all that the learning rate control problem would be strongly concave. But it turns out that, and it's not obvious because like this part on the right, it can actually be convex. So, you're now like log is obvious that it's concave, but this part may not be concave. So you're now summing things. You need alpha to be like high enough so that the log somehow, the concavity of the log wins over the term on the right, fundamentally. But it's strongly concave, which is like a prerequisite, I guess, for self-concordance. In particular, this is self-concordant, which means that we can actually find the solution to this very fast using Newton's method because of all the properties of self-concordance that I was mentioning. And also, it has like all sorts of like nice sensitivities to the regrets. Like if the regrets change by not too much, you can prove that the learning rate that's the solution of the argmax also doesn't change very much. And in fact, multiplicatively, if the regrets additively change by at most a constant, then multiplicatively the lambdas change at most by a constant. Okay, so you have like this nice sensitivity analysis. And finally, this is what we get. Like if you just piece together all of these, whatever, like machinery, effectively we're able to say that now if you start from, like multiplicative weights or optimistic multiplicative weights, and you put on top this learning rate controller that's uncoupled, if everybody does this, then the regret of everybody is bounded by at most a logarithmic dependence on time. Okay, and also logarithmic dependence on the number of actions. If now also people start not really complying with this, like somehow, maybe you don't know what the players are doing, you can still get square root of t, which is in, like kind of like the optimal rate in the case of, like if you don't know really what the other players are doing. So you kind of like don't lose anything by doing this, pacing yourself down. And if everybody paces themselves down, then everybody gets to equilibrium this implies a 1 over epsilon rate of convergence to coarse grained equilibrium, no matter the number of players, no matter the number of actions. Yes, I feel like this is like the main takeaway. It also turns out that for free-form games, like for sequential games, you also can use a kernel trick to simulate this algorithm without spending time linear in the number of actions, but only logarithmic, because you can like exploit the structure of tree-form strategies. So like you can also apply this method in a kernelized way, also for sequential games. Okay. And I guess like wrapping up, somehow like what are the important things here? Well, the idea is that we have a new uncoupled no-regret learning algorithm that is based on this kind of like dynamic learning rate control, like dynamic pacing of the learning. When everybody uses these dynamics, the regret is bounded by logarithmic in time. This significantly extends and strengthens somehow like the ideas in prior work. This can be efficiently implemented even in extensive form games using this, whatever, like kernelization kind of ideas. And I, want to stress again that somehow like the idea of agents differentiating behavior based on how they feel, like if they feel like too happy, too unhappy in the game, is not new. But I think what is new is the fact that for the first time, we're able to do theory about it and actually show that this leads to provably faster convergence to equilibrium, breaking the, something like the square root of t barrier that is omnipresent in online learning, because online learning studies adversarial settings. Our setting is multi-agent learning, which means everybody is learning, everything is non-stationary, everything is chaotic, but things are slightly predictable, okay? Things move slowly, there is smoothness in the system, we exploit the smoothness to get this log of t dependence on time. Okay, so this is like somehow you reconcile the lower bounds in online learning with this upper bound in multi-agent learning. Okay, I also want to say that since this paper, we also realized that somehow this approach is not just for optimistic multiplicative weights, but you can actually use it for any regret tracking algorithm. And even if players use different regret tracking algorithms, as long as they're all in the same family, this idea of pacing extends, right? So it's not, there's nothing special this analysis at Stock was really somehow specific for multiplicative weights. We were able to somehow, do the analysis in a different way that's not specific to multiplicative weights, and that applies to any type of regret tracking algorithm. So I think like that's also like an exciting kind of like development because it shows that this idea of pacing learners is not just specific to one algorithm. It's a general framework that you can now apply to your own optimistic learner and still get logarithmic in time dependence. So you can kind of like accelerate any learner by doing this. And I think with this, yeah, there's like some open questions. Can we improve the bounds? What about other notions of equilibria? What about like other classes of algorithms? This was only for multiplicative weights. I said this can be extended to regret tracking, but what about descent-based? I guess we don't know. I guess these are like obvious like next questions. Especially the last question makes sense in light of the fact that like descent-based algorithms behave very differently from regret tracking algorithms. This is the behavior of regret tracking algorithms. The last column is the behavior of descent-based algorithms, and you can see that regret tracking have like this kind of like cycling behavior that descent-based algorithms don't. So somehow like the two classes are a little bit different. We don't really know if these ideas extend from regret tracking to descent-based. We don't know. Okay, but somehow like the two classes are not really the same. And with that, I think that's all I had. Yeah, I'm happy to take any questions.
I apologize if this question was like already answered, but did this involve like when did you have any like RLHF, like any reinforcement learning? And if so, was it like you and the experimenters like doing that, or was it other outside people?
So I guess here there was no RLHF or anything like that. Like, and also in fact, somehow like these results are about learners. So, like somehow like algorithms do you implement, but somehow there's no humans in the loop here in any way, right? So this question is more about, okay, like what algorithms guarantee convergence to equilibrium? Like what algorithms can, like bots, for example, use to refine their strategy until equilibrium is reached? We don't know what happens if you include humans, but some of these techniques have been used with humans. Like, for example, in diplomacy, we were able to construct bots that reason and improve their strategy based on this not the technique on this paper, but like similar techniques, and then play against humans. And when you do that, though, when you play against humans, you have to be very careful about human-specific things like conventions and things like that. So there's like a whole host of like other techniques that need to be like taken into consideration before you can play with humans. But yeah, like this question is more like theoretical about even like the limits of multi-agent learning. Like even like forget about humans, but just like how can agents learn fast? Somehow that was kind of like the mindset. Mm-hmm. Yes.
Sorry, so what's the theorem? Because you said that in multi-agent the natural equilibrium is bad, right? So it's like hard to find. So and then when you learn the strategy of multi-agent is still independent. So what do you mean by convergence to the
correlated equilibrium? Yeah, it means it's the average product distribution. So like for Nash, usually what you do is that you for each player, you construct the average, and then you take the tuple of averages. Here, you first take the product of all the strategies of the players. Like this gives you like a tensor, basically. And then you take the average of those tensors. Right? So basically, the average product is a course correlated equilibrium, whereas for Nash interpolated zero-sum game, you would have the product of the averages is a Nash equilibrium. Right? But I feel like other than this kind of like transposing these two operations, it's the same. Right? But basically, the idea is that you can still extract from here a course correlated equilibrium.
One last question, or should we break?
Is there a? So I understand that this is good as I guess my question is, in a real situation, would the agents be motivated to adopt this as opposed to trying? If they're interested in their own utility, maximizing their own utility, they don't care about reaching an equilibrium.
Okay.
Would they be motivated to follow this algorithm?
That's a good question. Like all of this was from the point of view of minimizing regret and therefore converging to equilibria. It's not, like it's more the question of what does it mean to, as an agent to selfishly maximize your own gains. It's a little bit of a tricky thing, but imagining that really what you're trying to do is minimizing regret or computing equilibrium, like maybe you are interested in reaching a situation of equilibrium, then I think this is probably what you want to do. If somehow, like maybe you just really want to antagonize other learners, then there's other things that you can do. And there is like some recent line of of work on somehow exploiting learners and things like that. But I don't think that these techniques would go in that direction. I feel like you need slightly different things. Probably you need still learning dynamics, but I don't think that, like then the pacing yourself down so that the other people can catch up is the right, kind of like solution to somehow exploiting other players, right? Like you probably wouldn't want to pace yourself down. In fact, if you're winning, you probably want to win more. Whereas this goes in kind of like slightly the opposite direction, but equilibrium is achieved faster.
But you did have the result that it didn't hurt you in the adversarial setting.
Right. In the adversarial setting also, it doesn't hurt.
It doesn't hurt with regard to regret.
Yeah, with regards to regret, exactly. But yeah.
And then that's up.
Awesome. Hey, thanks so much.
Okay,
Thank
thanks
you.
again.
Yeah, thanks.
Right,